Hello.
Hi there. How are you?
Pretty good. I just created a diagram that I'm going to want to show,
Okay.
showing what Dialogus is and how it interfaces with the rest of the world. I need-
All right. Welcome, everybody. This is Open Research Institute's meetup for our projects. And what we do is we talk about what we have done, what we have planned to do, if we need any resources, and if we have any roadblocks. And I'm going to start off with some reports that have been given to me to share with everybody. And we have a big success with RockSat-X. This is the 2025 launch. It's a NASA program for universities. And earlier version of Opulent Voice was used and very successful. There's a updated video that shows kind of the whole experience that the students had. This is at the University of Puerto Rico. And special thanks to Oscar Resto for leading the students and including us and letting us help teach the students about digital communications and to give them an extra, really extended, nice thing for their scientific payload. RockSat-X project is for students to get some experience with a sounding rocket launched from Wallops, run by NASA. And in this particular project, the students develop a payload. The focus of the University of Puerto Rico has been on atmospheric sampling, and they have found some very interesting things over the past few years. And I don't think this year will be any different. So what we'll do is we'll share that video on this with this report. Puerto Rico, which is being transmitted in RockSat-X 2025 rocket, Phillips flight, Opulent Voice. Opulent Voice is an open source high quality voice protocol designed by open.
Test 20. Will 511 ignition set. Motor pressure. Test 30.
This is a report made by the students at the University of Puerto Rico, which is being transmitted in RockSat-X from
Nadia, we did it!
as a modulator. Opulent Voice is an open source high quality voice and data protocol designed by Open Research Institute for use in amateur radio. Apart from this radio experiment, the payload also includes environmental sensors capable of measuring humidity, temperature, and pressure in an effort to better detail habitability signatures of the upper atmosphere. This is WZ9XGX, Whiskey Zulu 9 X-ray Golf X-ray. RockSat-X, RockSat-X, RockSat-X 2025. This is a recording made by the students at the University of Puerto Rico, which is being transmitted in the RockSat-X 2025 rocket from Wallops flight facilities.
We have
Using
LOS on
Opulent Voice
GPS
as a modulator.
and no heat
Opulent
shield.
Voice is an open source high quality voice and data protocol designed by Open Research Institute for use in amateur radio. Apart from this radio experiment, the payload also includes environmental sensors capable of measuring humidity, temperature, and pressure in an effort to better detail habitability signatures of the upper atmosphere. This is WZ9XGX, Whiskey Zulu 9 X-ray Golf
It's a
X-ray.
lot of tracking.
RockSat-X, RockSat-X, RockSat-X 2025. This is a recording made by the students at the University of Puerto Rico, which is being transmitted in the RockSat-X 2025 rocket from Wallops flight facilities using Opulent. Opulent Voice is an open source high quality voice and data protocol designed by Open Research Institute for use in amateur radio. Apart from this radio experiment, the payload also includes environmental sensors capable of measuring humidity,
temperature, and pressure in an effort to better detail habitability signatures of the upper atmosphere. This is WZ9XGX, Whiskey Zulu 9 X-ray Golf X-ray. RockSat-X, 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 RockSat-X 2025. This is a recording made by the students at the University of Puerto Rico, which is being transmitted in the RockSat-X 2025 rocket from Wallops Flight Facilities, using Opulent Voice as a modulator. Opulent Voice is an open-source, high-quality voice and data protocol designed by Open Research Institute for use in amateur radio. Apart from this radio experiment, the payload also includes environmental sensors capable of measuring humidity, temperature, and pressure in an effort to better detail habitability signatures of the upper atmosphere. This is WZ9XGX, Whiskey Zulu 9 X-ray Golf X-ray.
And you can see the happy students. It's a really great video. So also, let's see. Okay, I have a DSES report. So a report from the Deep Space Exploration Society. There's been progress on the drift scan, and this is where you use an antenna, in this case DSES large dish, and all of the radio equipment for citizen science and for amateur astronomy. There's been progress on the drift scan. There was a software bug in GNU Radio module. Once this was fixed, then the drift scan data looked really good. It's good news. Tuesday, today, they're at the site and they're going to be setting up to look for the crab pulsar. And the frequency of note here is 408 megahertz. It's pretty faint and it's hard to detect. They expect that they'll need 5 to 6 hours of data to capture it, to be able to determine whether or not they can detect it. Now, after that experiment is done, then they'll put the 1.62 gigahertz feed back in, and Rick and the other folks are going to then install some new hardware and software. There's a list of things, just general maintenance, and also to move things forward for all of the different communications projects. So that's our DSES report. We have coming right up in September, we're going to be presenting at the AMSAT DL, or German AMSAT symposium. This is their annual symposium. It's a conference and they have a proceeding, and we will have a slot on Saturday, and we'll be talking about our work and sharing what we think folks should do for amateur satellite. And this is fantastic. It's a great experience working with all of these folks. Very much looking forward to seeing people in person that haven't worked with online, but never actually met. So this will be great. On Friday, there is a European Space Agency workshop for the Future Geo project. For more information about that, please look at our most recent Inner Circle newsletter for July. So you'll see our response to the call for request for information, request for commitment for the Future Geo project. This is funded by the ESA, and it is directly, of direct benefit to the amateur satellite community. So we'll be presenting our work and be part of that workshop as well. So big weekend coming up in September. There'll be lots to share about this. Okay, that's it for the reports. I think we have plenty to talk about for Opulent Voice. And if you're ready, Paul, we'll turn the floor over to you to talk about the things that have been going on in the lab over the past week.
So this is just a scrawling on the whiteboard, obviously, for reference, so everybody knows what we're talking about when we use these names that we created. The orange box shows the Pluto, which is doing the work, and I've divided up the ARM and the FPGA and the radio into 3 separate modules. The program running on the ARM we're calling Dialogus, and it's responsible for receiving the encapsulated packets coming over that USB Ethernet. and sending them to the FPGA for modulation. That's locutus in there. I didn't write that in. And it sends the samples to the radio to make actual noises on the air. And on the left side of the diagram, I've shown two different computers because that's the way I'm usually using it here at the lab, although they don't have to be two different computers. I've got Interlocutor running on a Mac Mini, which is the one I'm sitting in front of right now, and it has a microphone for transmitting purposes and a real honest-to-God Ethernet, which connects it up to a Raspberry Pi 5. And during actual testing, all I'm using the Raspberry Pi 5 for is a gateway between the Ethernet and the USB Ethernet. So I run an SSH connection all the way down from the Mac Mini to Dialogous, and also running Interlocutor on the Mac Mini. And Interlocutor is what uh, accepts the microphone input and creates the frames. So that's the context what we're talking about. And what we've done recently is to make improvements in this so that it's getting closer and closer to working, but we've still got some problems to solve. I forget exactly what the status was last week, but at one point recently, I filed an issue with the tracker, and the title was Transmissions Take 8 times too long. And that was going on uh, consistently with all the tests we ran, and that's not good. So what it looked like on a spectrum analyzer, which I don't have shots of, I probably should have if I had thought about that sooner. You could see a burst and then a gap and then a burst and then a gap and a burst and a gap, um, spaced way too far apart. And that matches to what we see when we instrument the code and measure what's actually happening. We were seeing a transmission that just took way too long and then another transmission. And after some struggle and some debug, discovered that that was actually what we had told it to do. As usual, we get the behavior you ask for. We were sending a buffer that was much bigger than the packet size. We're sending it with a IIO buffer push command, which takes the buffer out of user memory and magically copies it into kernel buffer, which then gets queued up to go out over the air. And we were using a buffer size that was not the same as the packet size. It was 1024 instead of 134 bytes long, and that all those extra bytes were being sent as whatever uh, was in the buffer, which was 0. So of course we got the result we asked for. We transmitted the packet, and then we waited about 7.6 times as long, um, transmitting zeros, and then we went on. So that problem mostly went away when we uh, switched from using the buffer push command to the buffer push partial command, which lets you send less than the whole buffer, and giving it an argument of 134. So it sent just the packet, 134 bytes. That reduced the amount of extra time greatly. It was back down to near real time on the transmission, but we could see there were still some glitches. It was not smooth and continuous transmission. And the goal then was to find out why and eliminate all those problems. And a lot of work ensued. And I think we found two different things going on, um, both of which need to be fixed. And maybe once we get the first one fixed, or maybe both of them, then we'll be able to reveal if there are any further problems with that. I instrumented the transmission across those Ethernets with timestamps, so I could see when they were happening relatively. I mean, just in terms of how long since the last time, and how long each call to IIO buffer push or buffer push partial was taking. It's a blocking call in the sense that if you call buffer push and there are no buffers free, then you're stuck there waiting for a buffer in the kernel to become free for you to copy your data into. There's 4 buffers in the kernel. That's the default. We've also set it explicitly just to make sure. And we should only need two. The one that's actually going out at the moment and the one that we're queuing up for the next packet time, next frame time. And so I believe, if I'm understanding this correctly, and that caveat applies to all this that I'm saying today, um, if things are working correctly, and we should have only two buffers in play at any given time, then the buffer push partial or buffer push operation should take essentially zero time. It should be able to copy the into the kernel in such a fast rate that you wouldn't even notice it with a millisecond timer, which is what I'm using now to avoid uh, having to do arithmetic in my head, basically. Um, and we'd see that some of the time, especially when it first starts after a fresh reboot and everything is cool. The first few buffer push partials take only 0 milliseconds. Sometimes it looks like 1 millisecond. But then things happen. I'll leave that vague for now. And that's no longer the case. We end up with the buffer push partial taking about 40 milliseconds, meaning that we had to wait for a whole frame to go out over the air to free up a kernel buffer before we could push more data to the kernel, which presumably means we've got 3 frames stuck in the kernel all the time. That's latency and not intended. So something's going to have to give with respect to that. The other thing I observed about this is that sometimes the duration of the buffer push call was very long, much longer than 40 milliseconds, maybe 80. 120 was a fairly popular value, plus or minus a couple, because we have some measurement uncertainty. Um, but often, sometimes 600 milliseconds or even up to a second, which is the timeout duration for a buffer push. And that caught my eye. I had no explanation for why that should be. So I did more research and investigation. And I should say when I say I really mean me and Michelle working together, and just say I for convenience of narrative. Um, we sent the we put more instrumentation in so we could see what was going on across all those interfaces, and we discovered something very curious. Um, Packets going across the real Ethernet, which I can measure inside the Raspberry Pi 5, they're going out like clockwork every 40 milliseconds, which is what you'd expect and what we intended for it to happen. But when you measure them on the other side of that USB Ethernet inside Dialogus, then that's not true. The packets don't get lost. They get delayed, sometimes for a long time, like 40 or 80 or 120, or sometimes even as much as 600 or 1,000 milliseconds. And it's not just one packet getting delayed, it's that packet and every subsequent packet. The whole timeline is shifting to the right. Like there's a gap in time where nothing's happening. It's not losing data. I looked at the actual data being transmitted, the payload data, and every payload is getting through in order correctly. Just some of them, sometimes it takes a lot longer than 40 milliseconds. And this accounts for measurement anomalies that we discovered earlier that we didn't understand, that the whole transmission was still taking a lot longer than it was supposed to from beginning to end. The session from when we get the first frame and generate the preamble to the end of the session when we get the last frame and generate a postamble. Um, it was taking much longer than it was supposed to, even after we had gotten rid of the buffer size problem. So I fear that there's something wrong with the USB Ethernet and that there's a fundamental limitation here that we're going to have to find a workaround for or even abandon using the Pluto in this way. I hope not. Um, but at the moment, we don't have a solution in mind for that. Um, so that's a big source of glitches and problems. Was there a question? I thought I heard some voices. Okay. So where was I? The This problem with delayed packets explains why the waveform looks raggedy on the spectrum analyzer, uh, and it explains big gaps that we can clearly see in the spectrum analyzer. Um, but it doesn't completely explain necessarily all of the little small gaps where a packet slips to the next frame. I think I understand what's going on there pretty well, actually, and have known about this problem since the beginning. We're just getting to the point where we can start to see it in the lab. I think the problem there is basically that we're trying to hit an impossibly narrow time window by aiming our packet reception time at exactly the frame boundary. So for that to work, it has to come in uh, from interlocutor dialogus, be packaged up and sent to the modulator all essentially instantaneously. And that, because of other delays, that works occasionally, works most of the time, in fact. Um, but every now and then there's a packet that takes a little bit too long because of the uncertainty and non-real-time nature of the various Linuxes involved here. And it slips over the boundary. So you get a frame that takes 80 milliseconds instead of 40 milliseconds, or even as much as 120. We can see that sometimes. Um, that I don't fully understand, but slipping Y1 seems like it's just a matter of that target window being too narrow. And I think we can solve that very easily by just backing up, adding a little bit of latency, like half a frame worth of latency, 20 milliseconds, move our target window to the middle of the frame, and then we've got plus or minus 20 milliseconds of buffer where we could receive a packet and still deliver it in time. Uh, we could also do something more clever and turn that in from an increase in latency to a decrease in latency if we can convince ourselves that the preamble doesn't need to be a whole frame long.
Is this an issue just due to um, the, the AXI bus not delivering data to the modem until we have a frame coming in? Is that why we're getting the gaps on the spectrum?
Uh, I don't think that's the cause. I don't have any reason to blame the AXI bus at the moment. Um, I think what's going on is all happening in C code up in Dialogus or possibly upstream from that.
Well, I
Uh,
guess I'm just saying if we're not sending data to the modem as we've designed it currently, then it'll just repeat the last uh, symbol over and over and over. So you'd go from a nice MSK waveform to a single tone, I think. Maybe.
uh, what we see is that it does get to be a much narrower spectrum, but maybe not as narrow as a single tone. And for the long gaps where we can actually see it on the waterfall display in the spectrum analyzer.
I see.
But
So this is where I think we need, just like a frame, modem level frame, and then if there's no data coming in, we can just send PRBS or something so that we have a continuous set of data to modulate.
yeah, and for a real deployment, you'd probably want to do that to paper over any remaining problems with frames getting lost or delayed. But right now, it's very useful that it's visible. And so I'm glad we don't have the fake packet that has the same spectrum as the regular packet.
Yeah, otherwise we wouldn't be able to really spot these sorts of problems. I mean, this is a kernel buffer problem, right?
We think so. We think a lot of it's kernel buffer, but there's I still think there's two things going on. Um, One I can't explain. That's these delays, which apparently happen in the USB Ethernet interface because I can measure them before and after. So somewhere between when Wireshark on the Raspberry Pi thinks the packet is going out to uh, that interface, which is actual Ethernet. Well, no, is the backside of the USB Ethernet. until that packet shows up as a available packet in Dialogus on the far side of the USB Ethernet. The timing changes in this radical way.
Just to be
And
clear, what you're talking about is the interface called USB quote unquote Ethernet. That's the
yep,
and you've instrumented on either side of the USB internet Ethernet.
that's correct. And there's a little bit more. I don't know what the drivers look like on either side or exactly how Wireshark gets its data on the Raspberry Pi 5 side of the interface. On the Dialogus side of the interface, I'm literally recording when it sees that packet coming in. So something that's metronomic turns into something with time slips, and that shouldn't happen. Um, I'm not sure exactly how to proceed on that. The only idea I have so far is to obtain a Super Pluto or a Libre SDR is another name that's given to it. It's you can buy these from AliExpress, for instance. Um, it's basically a clone of the Pluto design, but they've added a real Ethernet interface to it and made some other enhancements that are also useful. Um, but what we needed for this case is the real Ethernet, and assuming it's real enough, then that should eliminate all those gaps if they're being caused by the ARM, or excuse me, by the USB Ethernet, which is what it appears to be the case. And then all those problems will disappear, and we can see through to the other problems. The the timing problem, I think I've known about since before I even tried testing it. I knew that there was um, we needed to get control of the timeline so that the window for delivering a packet was hittable. I I asked Everest about what he was using for debug in the Pluto, and he says, "Well, I'm not actually using a Pluto. I'm using uh, what he described as some version of a Super Pluto that has gigabit Ethernet. It also has an SD card, so you can move images to it without messing around with transfers, which turns out not to be that terrible, but kind of a pain." Um, and some other capabilities, some more extra memory, so you can actually run a bigger installation. Uh, this may be exactly the same thing I'm looking at the Libre SDR. I'm not certain. Um, so I'm trying to order one of those. I had some problems getting the transaction to work last night. I'll try again here after this meeting and see if we can get one in. Um, I hope that that doesn't become the only solution. Um, Possible outcomes include every user has to have one of these instead of a Pluto. That would drive the cost up for users and also make it much less accessible. I mean, right now the Plutos are readily available. You can order this from DigiKey and get them quickly at a reasonable price. Um, for a somewhat higher price and all the pain of ordering from AliExpress, you can get one of these fancier ones today, but next month or next year, who knows? I mean, we can have reasonable reason to suspect that Pluto might be supported for several years into the future. So I don't want that to be the only solution for users. I would be okay if it was the only solution for developers, but
Right.
I,
I think
I,
that's what we're looking at is the solution for development is if the USB quote unquote Ethernet is causing us trouble, and I'm totally willing to blame Broadcom. You can sign me up to that. But if that's the issue and we can get around it by getting a development platform that actually has a real Ethernet hardware and it all of a sudden starts working like a charm like we want, since we don't have access to the hardware that's in charge of this, and since it may be inserting weird delays for development, that's fine. I think that eventually we should seriously be looking at making our own hardware or partnering with somebody that makes hardware, and that regular operators are going to buy that or build that, and we shouldn't worry too much about having to sidestep to buy another development platform, to buy a Super Pluto, to just confirm whether or not this problem can be eliminated by having real Ethernet delivery between the Raspberry Pi and the ARM that's running Dialogus. So I'm okay with that. I know that we would really, really like for people to be able to buy an off-the-shelf, inexpensive educational SDR in order to go ahead and just use it. But if it, we don't need to marry that idea. So we should be okay with saying, okay, maybe if this is the problem, let's determine whether it's not, and then we can act accordingly.
Yeah, I agree. Uh, we would, I mean, in the wonderful world of the future, when everything is perfect, there would be people knocking our doors down to help us develop. And if we can give those people a cheap solution that's readily available, like the Pluto, it'd be better. But that's still a relative handful of units compared to the number we'd like to deploy out to users. So as long as the users can use a Pluto or something access that we can provide, if we can come anywhere near to meeting the price point, then I'm happy about that. Um, this kind of somewhat sketchy clone Pluto from AliExpress is not an ideal answer, but it may get us a step forward. At least we'll be able to confirm or deny the theory that the USB Ethernet is causing the problem.
Right. That's worth the price by itself.
So this has been a little bit scattershot because I didn't have that outline clearly in mind when I started talking, but I hope I've conveyed the essence of what we're up to and where we're at right now.
Yeah, totally. Thank you so much for all of this work. It's been quite the adventure over the past week, and been really great to work with you.
Thank you for your help.
Okay, and then we should turn our attention to some recent discussion about the actual FPGA MSK modulator and demodulator. And I'll turn it over to Matthew, because I think you've read all of what's going on and or the authoritative source for this. So you have the floor.
All right, thank you. So yeah, I've been trying to catch up with the chat on Slack, and I know that Pete's been working on trying to run the BER simulations, and he certainly has some, I think, good ideas for alternate demodulator approaches. I still like, finishing our current approach, because I think being able to tie the architecture to a particular paper is still very instructive. I mean, it's one of the reasons I was pursuing this, because it's nice to match the theory and what a paper's saying to an actual implementation. So I think it's still worth pursuing, but I think, in the end, and my thought is we could implement other architectures and other things on top of this. We have a foundation for doing that. So I think these are all very good things. As far as the particular concerns that Pete's been having, I think I need to probably have a little bit more discussion with him. I don't think the way he's understanding the phase frequency detector, it looks correct in the equations, but it's not matching my intuition of what's supposed to be happening there. And I have some equations I'll share with him to try and demonstrate that. So I don't think we have 180-degree phase ambiguity as he's seen, but we'll just continue working through that. I don't think we've seen that, but even in real world implementations, even if you have 180-degree phase ambiguity, it's not going to stay 180-degree phase ambiguity for long. So I think, I've never seen a case recently, that we haven't locked. I think it's been pretty robust in the modem locking and the two loops locking properly the way we would expect them. So I'm not sure there's any, particular issue in what he's finding. I think it's just a good exercise to make sure we've not missed anything And, if there's something he uncovers that is a deficiency, then we can certainly address it. So I think that's the main issue or the main discussion that we've been having is how the phase frequency detector is working in the demodulator. Beyond that, I'm still trying to get back to some of the simulations and RTL design to make sure we're, if there's any deficiencies there, I'm concerned there's a couple of things that can be improved. So I'm trying to get back to working on that. So I think that's all the update I have for today.
Wow, that's plenty. Yeah, no, looking forward to it. There's been really good discussion on Slack about all of this and some great questions and enthusiasm. So looking forward to seeing how the modulator and demodulator can be developed and improved. And also, I definitely agree. I think that the sort of the classic approach from Hodgart and Massey and others being brought forth and here it is in VHDL and working for, we've had really good success with this particular design, and that having it there, having it published and where folks can look at it and actually run it is of great value. So yes, it is a classic and older design, and yes, there are some ways to update it, going from two numerically controlled oscillators to one. I think to me stood out as the biggest. Hey, why don't you do this rather than that? And that we're going to move forward and explore the way that Matthew has designed this this communication system is part of a sort of a broader approach that he brought to ORI of a modem module approach, so a modular modem, and using sub modules in GitHub to stand for the different components, so that you bring them in at the top level, you stitch them together, and they all work together to create a radio. A lot of people spend a lot of time talking about modular designs. Actually executing a modular design, a clean modular design, is really hard. We have one, and I think that this is an opportunity for us to actually show how this works. So all the different submodules that make up our MSK modem for Opulent Voice, they all kind of work together and are put together in this top level repository, Pluto_MSK. So it looks like that the modulator and demodulator, the actual MSK modulator and demodulator, could be you could have an alternative if you wanted to update it for the single NCO type of case, and then they would then be stitched together with all the other parts that already exist, like the PI controller, the EMA stuff, the PRBS stuff, all of that still need it. So this just shows kind of this sort of the resiliency and the usefulness of approaching the design in a true modular way. So I'm looking forward to this, to seeing if we can explore and get get some alternative parts in there, and to kind of show off the flexibility of the modular design. Having here's the paper and here's the implementation and here's sort of the classical approach is very powerful. So that stays and has already been of use. So already been able to point people to this repository who are like, it's a mystery, MSK, great. I can see a couple of YouTube videos that are very surface, very superficial. And, there really isn't a good implementation of this that's open source. So we already have one that's already proven super useful. And okay, so we need another one and, bring it, I guess in a more modern context or more digital signal processing emphasis. Great. So I think it's a win. And yeah, it's a both and not an either or sort of approach. All right. I think that's all I've got. Any other questions or comments before we close for the week?
I have one or two.
Oh, sure. Go ahead.
One of the things that I'm able to instrument is what I call the AXI S transfer count delta. which I was just going to look up and see exactly how I derive that. But it's a register read. I think I subtract two register reads. That's what I'm guessing it is. Um, but I don't really understand exactly what that means. And I don't get um, results that I'm expecting from it. So, Matthew, are you able to enlighten me on that?
Yeah. So what was the question again?
Okay, so I'm reading the Axie S transfer count
Right.
before and after uh, a buffer push, and then subtracting. Um, what does that tell me exactly?
Okay. It's going to tell you the number of data chunks, if you will, that were transferred over the AXI bus. So I think we're transferring bytes currently. So it would be the number of bytes that were received from the modem at the modem TX from the AXI bus.
That's what I expected it to mean.
Now I haven't spent a lot of time simulating this, so there's could easily be an error here.
Okay, so there's a couple of different patterns that I see. The one that I think of as being the healthy pattern is that I get 66 or 67, um, which is half of the 134 byte um, frame that I'm actually sending. But maybe that makes sense, I think, because what it's counting there is IQ samples, right? So 32 bits worth of data. And what I'm sending is uh, two copies of the byte data. So that I think that explains a factor or two.
Yeah,
But
so but it's not IQ, right? I mean it's just it should just be data words. Um and so yeah, I
right,
just confirmed in the RTL that we're just counting the number of effectively valids on the AXI bus during that transfer.
okay. So
So
how big is the transfer that is being counted there?
so I'm um so if that's 67, then it was 67, 66 or 67 um data words that were transferred. And now the only other thing I would say is what are we defining as a data word? Well, you're sending 32 bits at a time.
Well, I'm not sending anything at a time. I'm at my level, I'm packing the buffer with 134 bits, excuse me, 134 bytes of data. And um, when that gets pushed into the FPGA, I get two copies of each byte that I put in. Uh, my sample is my number repeated twice, and then that goes out to the buffer push. If this is all invisible, IO doesn't understand this, but we're transmitting data bytes as if they were uh, samples. And what it expects,
I
I
mean,
think,
well, we're talking about the MSK modem, right?
yeah.
So we're transferring bits effectively, right? Organized as bits as bytes or words or double words. I and so we can configure in the modem for how many bits are being used, right? So it's 128 bit bus, but we're using 8 bits or 16 bits or 32 bits of that bus only. Um, and so that's configured in the modem config in the transmitter configuration. And then so when a AXI transfer is initiated, um, we'll start counting each transfer, which is defined by a valid pulse on the AXI bus. And so at the end of the transfer, we can read back that value and see how many transfers occurred. And so it's the transfers aren't telling us how many bytes or bits or anything. It's just telling me how many transfers occurred. So there could be 128 bits each transfer, or there could be 1 bit each transfer. Just so that's how we're defining it, right? How we're using the bus is kind of different. Okay, so say we were going to send 100 bytes and we were sending eight bytes or 8 bits at a time, or 1 byte. So then there should be 100 transfers. But if we're sending double words, then there would be 50 transfers, or if we're sending words, 50 transfers, or double words, it would be 25 transfers, right? So so the number of transfers should just match how we're packing the data into the 128 bits to send the whole block. Does that make sense?
Yeah, I think it does, and that matches my understanding. Um, if it's 32-bit transfers, I think. Um, okay, so sometimes I see that, and sometimes I see bigger numbers, like much
Yeah,
bigger
okay.
numbers, and sometimes
So
I
what
see
could be
very
happening
small numbers.
is we're only resetting. So this could be an improvement, actually. There's no way on the AXI bus to say, oh, this transfer is completed. Capture the count, right? So it just counts indefinitely until there's a AXI reset. And so the AXI reset will reset that transfer count. So it's probably not as useful at the moment. But whatever you're reading back should be some multiple then of if each block length is the same, then what you read back should be some multiple of that block length, right? So we might want to add a register to clear that counter independently, so that after you complete a transfer, you can clear it, and then when you start the next one, you'd be able to read it back and have it be a useful number.
Then I'd have to deal with the timing of the clear operation as well. I wonder if
Yeah, or if we have some other mechanism we can use to clear it. I mean, we could potentially, if the block of data has like a defined header, we can detect that potentially and reset the count. Then, yeah, we'll have to think about how we can make that more useful.
so the number I want to see is 67, because it's half of 134, I believe. And the sometimes it does that. I'm looking at a test run that did that right now, but often I also see long runs of 66. Maybe that's just my timing, that I'm not necessarily grabbing the value in between transfers. Um, the actually transfer doesn't happen all at once, right? Or does it? Is it a burst when the data is available, or is it actually being metered out as the modulator uses it?
Yeah, so the modulator is asserting the ready signal when it's ready for another piece of data. So basically, it's throttling the AXI bus through the ready signal.
Okay, and so those should be like spread out in time, like 8-bit times apart or something like that forever. And they should never be
Right.
bursts of them.
Right. Yes.
Okay. So detailed timing will account for small changes. That's good. That makes me more comfortable with this number. But if I'm getting very small numbers, like I repeatedly read that register and get the same value later, that means that nothing's happening. Nothing's being transferred during that time. And
Yeah. Yeah.
what are the possible causes of that?
So if we're expecting transfers to have happened and that value is not increasing,
Yeah.
um,
Or
boy,
increasing very slowly.
yeah. So I mean, like I said, so that count is every time there's a valid and a ready. So basically, every time there's a valid on the bus, and the modem asserts the ready signal to receive a transfer, we increment that counter. So, I'm not, so barring any bugs, which are certainly possible or likely, then if that counter is increasing very slowly or isn't increasing at all, it's indicative of no transfers occurring, which sounds like is not what you're expecting.
Right. Yeah. And no transfers could happen for two reasons. Either the modem's not ready or there's no data in the buffer yet. Right.
Right.
So if I claim that I've just pushed you 134 bytes and then 40 milliseconds later, you still haven't done any data transfers, then either those bytes didn't really get pushed or the modulator is in some weird state where it's not really running.
Yeah.
Okay.
Yes.
All right. That's helpful. I think I understand it a little better now. I'm not sure what to do with that knowledge right away, but maybe it'll become useful. Thank you.
Well, I mean, if there's certain things, diagnostic features that would be useful to you, I mean, I think we can throw them on the, put it in Slack or put it on the Trello card, and I think we can certainly add diagnostic capability. It's pretty minimal at the moment, but it's very much, it's very important to get that visibility. So anything that would be helpful, we should go ahead and put it in.
Okay. I will keep an eye out for opportunities to do that. I think that's all I had, Michelle.
Okay, cool. Wow. Okay, lots. Thank you so much, everybody. This has been great, and the next couple of weeks are going to be action-packed, and we'll get ready for some big presentations. Looking a little bit further into the future, we're being asked if we would like to help set up a sort of a radio frequency village at San Diego B-Sides, which is a cybersecurity and wireless security conference through the DEFCON community. And it's going to be anticipated to be at San Diego State University. And then we have some other requests for presentations to the Japanese AMSAT community. So following the upcoming presentations to AMSAT DL and with the ESA, JAMSAT would really like to know more too. So that will probably be over remote links like a series of Zoom calls, or participation in one of their upcoming things. In October, there will be the LibreSpace Foundation's Open CubeSat workshop. We did not submit anything to present there, just mainly because of the pretty busy schedule for the summer and early fall. But I think that anyone watching this that's following along with what we do should probably register and intend on checking in and participating in that conference. So maybe we'll be able to share our work with them just from a sort of a participant point of view, or just a general community point of view. Yeah, and plenty of other things coming up over the next 6 months or so. So thank you, everybody, for all the hard work. Could not do ambitious things without you. And as you can see, we're getting a lot of successful stuff under our fingers and getting traction on the things that need to be got traction on. So until next week, and let's see you on Slack. Thank you, everybody.
Please hang up and try again.